All right, so now what I'm going to do is do a demo, and I think what I'll do is start with the SIM detector, and just show you some of the stuff with that, and then go on to this point gray camera there. So I'm running on Windows. You guys are going to be running tomorrow in the lab, and I'm going through a set of demonstrations that more or less correspond to what's in the lab for you guys to do hands-on tomorrow. Not exactly, but we'll cover most of the same territory. And in the lab, I think you can run, some people will be running the SIM detector, many people will be running real Prosilica cameras. And I'm running MEDM, you guys will be running CSS. We'll both be running ImageJ, but you guys will also be displaying images in CSS as well as ImageJ. So I've got a shortcut here that basically just CDs to the IOC boot directory for this SIM detector and then starts the SIM detector application. And then this is going, up here is going to launch MEDM. I'm going to kill that window. For now, we don't need the IOC window, don't need this main MEDM window. So now, this is a top-level screen for area detector, which basically has the ability to launch any of the detectors that are in the package. You guys probably wouldn't use it, but I do. So I'm going to launch here the simulation detector. And it's configured right now to do 1024 by 1024 images, unsigned, 8-bit. Right now it's doing, let's switch it to mono to start with. That was doing RGB, color image. I'm not going to worry about a shutter. So right now the exposure time is set to a millisecond. The period is set to 50 milliseconds. So when I start it, I should be collecting 20 frames a second, determined by that 50 millisecond exposure time. So right here, you saw I press this button, the start button to start it. I press the stop button to stop it. Right now it's in continuous mode. If I go to single mode, then every time I press it, it just takes one image. I can go to multiple mode, and the number of images here is set to 100. So when I do start, it'll collect 100 images. That should take 5 seconds, and then stop. So most detectors support that. Single, multiple, continuous. I'm going to go back to continuous here. So you notice that I did put the name of an XML file in this field. That's called simdetectorattributes.xml. And that file could have a path in front of it. The default working directory for the IOC is the IOC boot directory where it started. And that's where this file is. And so let's go look at that file. I think I have it loaded here in, can you guys read this? Or do I? Let's see if I can. Is there a zoom in this? Is there a view? Oh, there's view. Zoom. Oh, zoom in is control mouse wheel up, or control mouse wheel up. There we go. Okay, so I've defined, roughly a dozen attributes here. And so for each, so this XML file, you say attribute name equals, and that's the name of the attribute. I believe that can't have any embedded spaces in it. And then the next thing is the type of attribute. So type here is EPICS PV. And then source equals, so that's going to now be the name of the PV. And so this is the acquire time, right? So this was, in this case, 0.001 seconds. The DBR type, so you're basically telling it, what data type do you want this parameter to be? If you say DBR native, then whatever the native channel access type is, PV type, that's what it'll use. And then you can give it also a longer description of, camera acquire time, or any string, so that's more descriptive than just the name. So the first 4 parameters, and then there are a number here of PVs, like this would be the storage ring current at the APS. That's not going to work with my computer here, but it doesn't generate an error, a fatal error either, but it's not going to be able to connect to that PV. And then a storage ring current engineering unit. This is the energy of an undulator at the APS and its engineering units. It's not going to connect to those. I don't have any PVs, I think, here on your control network that I can connect to. So we're just going to do things that are local to this IOC. So you can get things that are PVs. You can also get things that are called parameters. And these are characteristics of the driver or plugins that are being run in this IOC. The only reason to use a param versus an EPICS PV is that there's essentially no latency. If something is being updated as an EPICS PV, let's say at 500 frames a second, the value that you get for it might not be the one that's appropriate for this frame, right? It could have a few milliseconds of latency in channel access. But if you get it as a parameter, you're guaranteed to be the most recent version from the driver. And then here's a couple more that are EPICS PVs. And then another one that's a parameter. So this is the manufacturer of the and then there are some you can write functions, and so these are just some functions that return, pi and e and the Gettysburg Address and just to show that you could do functions. Okay, so those are the metadata that's going to be collected with each image. It always also collects metadata. There's stuff about the array, like the unique ID and the timestamp. You don't have to put that in here. That's automatic. This is only things beyond the parts, the things that are standard in the ND array. And if you want to change that file, you edit it and, edit that file and just hit enter here or just restart the IOC. This is where you would set up the simulation, the sim detector. So right now we're doing a linear ramp. Okay. And if we open, this is the all plugins screen, common plugins. So let's first look at this using the channel access viewer in ImageJ. So the ND plugin standard arrays is enabled. And if I go here in ImageJ to plugins, EPICS area detector, EPICS AD viewer, it brings up a log file here. And I can't read this, so I have to move it. This says 13PG1, so that's configured right now to look at the point gray. I need to change it to Sim1, and I think I made it. Oh, I did Sin1. There we go. So I did 13 Sim1 image 1, and that's the name of an EPICS PV for the waveform record. And now if I do start, okay, so that's now updating this simulation. You can see that this is a linear ramp, and it's just adding 1, and it's 8-bit data, so it overflows. So every time it gets to 255, it goes back to 0. So that's why it's these bands that go from black to white. And it's just adding 1, or it's adding some number to each pixel at 20 frames a second. If I change the exposure time to 10 milliseconds, all of a sudden those stripes get closer together because it's adding a bigger number each time. If I go to that simulation setup and change the X gain from 1 to 0.5, the stripes change their orientation. If I now change this from a mono image to an RGB1 image, so now it's in color, and I can change this. So right now the red gain is 2, the green gain is 1, and the blue is 0.5. If I change the blue to 3, now the colors change there. If I change this to the peak mode, so now it's got it's putting a peak at position 500, 500. There's only got one peak in each direction. The width is 19 in X and 90 in Y. It's not going to show up here until I increase, it's now multiplied. The intensity of the peak goes with this gain. So let's set that to 200. Yeah. And let's go back to mono mode. Okay, so now we have a peak that's asymmetric because it was 90 by 19. We change it to 19 in each direction. It's now round. And then we can add here some noise on that and some variation in the intensity, like 10, let's make it 50 so we see it more. Yeah. And now it's occasionally going bigger than 255, so it's wrapping around to 0 in the middle as the peak intensity varies there. All right, I think that's enough for the simulation detector. Let's see. I got a list here. I want to make sure I go through these things. Yeah.
In image, we can view the processed image also. Right?
Sure. Okay, so right now this standard arrays is getting its data from the from the SIM1, which is the main detector. Let's go make a look at the first region of interest. And it's defined here to start at pixel 900 in X. Let's make it a little smaller, like 400. I'm going to switch this back to a linear ramp so I don't have to aim my ROI as precisely. Where is that? Oh, I closed it. So let's change this to a linear ramp and change that gain back to 1. So now if this region of interest starts at 400 in X and it's 200 pixels in X, starts at 700 in Y and it's 150 pixels in Y. This plugin is currently disabled, so I need to enable it. And it's, so now we can see that the output image is 200 by 150 pixels because it's the size in these two directions. Right now, that isn't going anywhere. But if I go to image 1 here and I change it from getting its data from SIM1 to ROI1, now now we're only seeing the region of interest, right? we've changed the plug-in chain, so the standard arrays is getting its data from the region of interest. Now if I go to my region of interest and set the size in X to be 300, this updates to be bigger, and I could change it to reverse it in the X direction. So now the thing is moving the other direction, reverse it in Y. Yeah?
So this is kind of a meta question, but what is the best way to move sound from not having a screen that looks like a deck of cards?
That's a good question. What people do on our beamline is the beamline scientist designs a screen that does what he wants the users to see 90% of the time. And then there's a more button where they can pull these up, right? So, I mean, when I build these screens, I would call them engineering screens, right? They expose everything. I try to make them so that they're understandable, but they're not what you want a user to have to deal with most of the time, unless they're an unusual user. So, right. You need to make custom screens. The nice thing is at least you've got all the elements here. It's kind of cut and paste, right? To take the things that are important and put them on a screen where you only see the important things. Okay, so let's put this back. Well, no, let's go to a transform plugin. Open that one and enable that and change this channel access plugin. So instead of getting its data from ROI1, it's getting it from trans1, the transform record. That, is currently set to have the null transform. So it's not doing anything. So the image looks just like it did. But if we rotate it 90 degrees, now it's doing that, or rotate it 180 degrees. And one of the things you can see here, well, if we do no transform, the execution time in milliseconds is about 0.1. So it's taking about 100 microseconds to just pass the image through without actually doing anything to it. If I change it to rotate 90 degrees, it jumped up to about 2.3 milliseconds. If I go 180, it's down to about 600 microseconds. So you can see that each of the operations has a different level of arithmetic complexity and how long it takes. Rotate 270 degrees, it's back up to 2 milliseconds. Mirror operation, 600 microseconds. Yeah. So these are all the 8 operations that you can do. So it's pretty fast, right? And that's doing it on a 2-dimensional image. It will also work if we do this with RGB. So now it's rotating a 3-dimensional image, and you see this time jumped up from 2 milliseconds to like 6 milliseconds, right? It's taking longer for an RGB image. Okay. So in the SIM detector here, and this will be true for many detectors, right now my acquire period is 50 milliseconds. If I change it to 10 milliseconds, so now it's doing 100 frames a second. And if we go to the let's go to the statistics plugin. Let's disable this one and enable the first one. All right, I'm going to turn off all the statistics initially except the basic statistics. Right, so you see we know it's receiving, the detector is doing 100 frames a second. Like, it's actually a little over 100 frames a second. And the statistics plugin here is only doing 38 frames a second because the execution time is 28 milliseconds, something like that. So it can't keep up, right? It at 100 hertz on these RGB images. If I slowed that down, if I changed it back to mono, the statistics plugin went down to only 2 milliseconds to execute. So the RGB is taking it a lot more time. And now it is keeping up. So, but now if we turn on some more calculations, like calculate the centroid, that is now taking 5 milliseconds. If we also calculate the profiles and the histogram, it's up to about 8 or 9 milliseconds. So it can still keep up at this frame rate. But let me make the frame rate a little faster. So if I go to 005, and I'm doing that now, it should be it's doing 200 frames a second. Now this thing can only do at 8 or 9 milliseconds, it can only do about 100 frames a second, 110 frames a second, right? So it can't keep up. So now you see our queue, our number of free elements in the queue here is 0 because it's processing 100 frames a second, but it's receiving 200 frames a second. So it's overflowing the queue. So let's see what happens if we go to the more screen and we say right now callbacks block is no. So it's just putting the elements in the queue. If I say callbacks block yes, it's still doing 100 frames a second, but what you'll see is that the detector now is being slowed down. So the detector, instead of doing 200 frames a second, is now only able to do 100 frames a second because the detector thread is now what's doing the statistics calculation. So we've slowed the detector down by saying callbacks block equals yes. But now our queue is okay. If we let's go back to callbacks block no. Let's stop this and increase the queue size here to 200 and tell it we want to collect 200 images. This is the example I was talking about earlier. So, and go in not to continuous mode here, but multiple mode. So now what we should see is the detector is going to collect 200 images. It should take about 1 second, right? Because it's doing 200 images a second. And we should see this number go down, the number of free elements, but it shouldn't get to 0, right? Because the queue is big enough to store even if this was really slow, this queue is big enough to store 200 images without running out of space. So let's see if that's true. So you see that number drop, and I don't know if you can see it, but it's at 200. It's now dropped down to about 100 and then back up to 200. So it was, it put about 100 elements into that queue, and then the detector stopped, and then the simulation, the plugin finished processing those 100 elements that were in the queue. So that's how you can, at runtime, manipulate the size of this queue. If this was a file-saving plugin, we could be buffering however many images you need to save without dropping any, even if your file writer can't keep up with your detector. Okay, I think I'm going to kill this sim detector IOC. and open instead the close this. And start the point gray detector. Okay, so that just launched the IOC for this camera here. And now I need to pull up its MEDM screen, which is this. And right now it's set. So in this case, you can either enable or disable the frame rate. So if you disable the frame rate, then the frame rate is controlled by the exposure time. In other words, it goes as fast as it can, consistent with this exposure time. Or you can enable the frame rate. If the frame rate is slower than the exposure time would dictate, it'll collect frames more slowly. If it's faster, it'll change the exposure time to get to the frame rate that you've asked for, if that is indeed an attainable frame rate. So right now it's off, and my exposure time is 50 milliseconds, so this should be doing 20 frames a second when I start it. Yeah, so it's the image rate here is 20 frames a second. So in this one, I've got the channel access plugin here disabled and the PV access plugin here enabled. And so in ImageJ, I'm going to select the other plugin, which is the NTND array viewer. That's the PV access viewer. And it's connected to the point gray, and then I'm going to start it. There we go. All right, you're all on TV. If that's too annoying, I can move the camera. Just get the top of your heads or something. We'll just get the ceiling. No. Whoa. That's true. Either change, I got to see if that's an image. So in ImageJ, if you want to change the brightness and contrast, I mean, there's a menu item to do it here, edit, image, adjust brightness and contrast, but you do that so much, it's Control-Shift-C, brings this thing up. And you can see from this histogram here that it's saturating. So that's, I need to decrease the exposure time. So that's here. Yes, I could change it to auto. So if I go to properties here, so this is a screen where there's a lot of different properties here, many of which are not displayed. This thing is smart, and it asks which properties are actually available in the current configuration of this camera. And if they're not available, it hides them on this screen. So there is an auto exposure you can turn on, and then there's a thing where you can push a button and say do it once, or you can say do it continuously. This is probably the thing that people make the most mistakes with the point gray camera, because it's on and they don't know it, and they try to change the exposure time and it won't change. And the same thing is true of the frame rate, because you can make the frame rate auto. So I usually don't use the auto exposure. I just tweak it manually. And a lot of times in scientific work, what it thinks is a good exposure is not showing you the interesting thing at all, right? So, okay, so 20 milliseconds, actually still a little bit saturated. So I'm not going to turn on auto exposure. And let me make this window a little smaller so it doesn't hide everything. So maybe 10 milliseconds. Wow. Okay. And we'll catch the reflection. All right. So there's lots of controls here we could look at. Here's for instance the gain. So if I increase the gain on the camera, it gets brighter. I usually run it at minimum gain, and then just adjust the contrast and the intensity levels in image J. Let's see. This is the stuff for triggering. We're not going to play with hardware triggering today. Just trigger an internal trigger. There's some status information. So if I stop the camera now, it's giving you the temperature, 49 degrees C, and it also says that there were 97 dropped frames. So during that whole time that this has been running, when we were collecting hundreds and hundreds of frames, the USB wasn't able to keep up on 97 of those frames. They were dropped. Usually, if it's set up right, I can collect the whole tomography data set without a dropped frame. But you do have to have a computer that's powerful enough that the image it's not too busy, that the USB driver gets the priority it needs to not drop frames. See what else I want to. Okay, I did that. So right now this is collecting raw 8 images. And image J is telling us that these are, you probably can't read this, but it says 8-bit images, 2.2 megabytes. So I can change the camera here from raw 8 to, let's say, mono 16. So now these are 16-bit images, and image J says it's 16 bits. If this were channel access, that wouldn't have happened, right? But because this is PV access, it's now sending a 16-bit array instead of an 8-bit array. And it can't quite go as fast. It slows the camera down a little bit to go at 16-bit mode.
Can you do the same on the status?
Yes.
Change the color mode apply?
Yep. And you can also, with the point gray cameras, the camera itself is actually only a 12-bit camera. It's not a 16-bit camera. But it can send 16-bit data, but only the first 12 bits are significant. But it's taking up 16 bits worth of USB bandwidth. So one thing that you can do with these cameras, which is nice, is you can tell it to collect raw 12-bit data. So now what that does is that it takes it's sending 12-bit data across the USB. Area Detector doesn't know how to deal with 12-bit data. But once it gets into their library, you can convert raw 12 to raw 16. And now you're getting the full resolution, the full dynamic range of the camera, the 12-bit data, but we were only getting 75 frames a second when we did mono 16, but now we're getting 90 frames a second. So we've got the optimal trade-off between bandwidth on the USB. We're taking advantage of the full capabilities of the camera, but running it faster than we would otherwise be able to do. I don't remember if the Prosilicas have a 12-bit mode that you can read them out. It may only be 8 and 16. I don't think they have this 12-bit mode. Yeah. Okay, so maybe we'll go back to mono, or back to raw 8. Okay, what's the next thing I want to show? Okay, I'm going to show you an ImageJ thing, which is that one of the things that comes with area detector is this thing called a Gaussian. Oh, first I have to draw a line. So let me draw a line through that bright stripe there. And here's a Gaussian profiler. So it's trying to fit a Gaussian along that line and telling you, what the full width half max and the centroid of that Gaussian is, and doing it in real time. So this is a real-time plot of the intensity along that cut and a Gaussian fit to it. It's obviously not very close to a Gaussian, but it's somewhat Gaussian. It's closer to a square wave. Yeah. Yeah. No. Yeah, that's just a little thing written in Java in ImageJ. I'm not sure. Well, actually, we can look over here. No. So ImageJ here is displaying 28 frames, 29 frames a second. And whereas the camera is collecting, what is it doing? 95, 90-ish. So this is not keeping up.
Why are there those dips sometimes? What's going on there? Shaking the table. Oh, you're shaking the table. Okay.
Is that right? Yeah. Oh, it's a second hand. Oh, yeah.
Oh, that's the second one. Oh, okay, good.
Mark, I have a very simple ethics question. You tell ImageJ where to get this screen from, this image. I would expect it to say something like get it from cam 1, because that's the ethics name of your camera. But somewhere you lost the cam 1.
Correct, because we could have multiple cameras in this IOC potentially. So it's the name of the plugin, because we're not getting the data from the camera. We're getting the data from the plugin. And so we're getting it from this PVA plugin here. And here it tells us the name of it is 13PGA1 PVA1 image. That's where you find out what the PV name, well, the PV access name of this is. Yep. And see, in this plugin, there's in fact nothing configurable at runtime. Right. This is the standard base class stuff, and this is just some information.
How important is it to be unique with regard to the async port and also there's another point, the array port? Are those intended to be unique identifiers?
They only have to be unique in so this asyn port and the array port. So these are the names of the asyn port drivers in this IOC. There's one for the camera and there's one for each plugin. And they must be unique in the IOC, but that's it. Right? So they don't have to be unique on the network, they don't have to be unique on the computer, just in that process, that IOC process. Those names are unique. If you try to create a plugin that has the same name as another one, asyn manager will complain. It says you can't create that port because it already exists.
But you can have multiple cameras on the same IoT, you said, right?
Yes, you can.
And they would use the same array port, or they wouldn't coordinate something?
No, one would be called, this one's PG1, the other one would be PG2. Right, but you could switch which camera you're looking at by just changing this from PG1 to PG2, right? Or if they're running in separate IOCs, then you change it here from PG1 to PG2, right? So you change the client rather than the server.
Can you view multiple detectors in ImageJ?
Pardon me?
Can
Yes, yes. So I could launch another instance of this. Now they happen to be looking at the same camera, but I could change this one to be looking at a different camera. You could also launch a second instance of ImageJ, which is probably a better idea because, I mean, one of the nice things about ImageJ, let me kill this one, is that as I move my cursor around here, it's showing me the intensity at that pixel. I think if you have two windows open, it may get confused, as to which one is it supposed to be showing here. We're really like abusing ImageJ here. It's not what it was meant to do, display images in real time, but it does an amazingly good job of it. But there's a few things that actually don't work that well. And one of the things, as I move the mouse here, it is changing the intensity. But what I've found is that when I move the mouse, and it's showing you the X and Y coordinates, it doesn't track perfectly if this is a live display. So if you want really accurate pixel positions here, what you want to do is to hit stop the live update. Now these, excuse me, X and Y pixels, they track perfectly. So like when I'm doing tomography and I want to say where's the left and right edge of my sample, I'll stop this display, measure those two positions, and then start it again. That's one of the things that it could probably be fixed in ImageJ, but it seems like it doesn't track the cursor very well when the images are updating frequently. But there are lots of nice things that ImageJ does give you, like the ability to go, you just hit the plus key, zoom, 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 zoom out. And another thing that ImageJ gives you, let me zoom in a little bit here. See, if I say capture, if I press this button, capture to stack, now it's going to take every image that's arriving here and stop that. Wait, what's going on? Oh, I was stopped. You're right. Thank you. Oop. Huh. What happened? Right. Kill that, reopen it. The IOC is still running. PVA is still running. Why didn't that connect? That's weird.
Do you have it as an instance of this of the meeting? Maybe just combine those two connections?
No, it's only got one. I did open a second one. I don't know if that was a problem. Let me just restart ImageJ. It's the demo effect. Okay. Huh. Oh, now it's done. Okay. So now I hit start. Shrink it one level. Now say capture to stack. And now stop capture to stack. Stop. So what that did was collected all those images. So now see this scroll bar here? Watch time go backwards. Right? And so now, you've basically collected a movie in ImageJ, which you could use ImageJ to say, file, save as, AVI. So you could save that sequence of images as a movie that you could then, put in your PowerPoint or whatever. It isn't necessarily the best way to do it, but it is a way to do it because we're... What's that? Because we're saving it over PV access, we haven't been guaranteed that we've captured every frame, right? In fact, I'm pretty sure we're not capturing every frame because the cameras and the plug-in here is doing 92 frames a second, but when I start this, it's only doing 22 frames a second. That's partly because let me bring up my my task manager here. We're getting close to saturating this computer, and if I look at the processes here, Image J is using close to 25% of the CPU, which is one core, because it's only a 4-core machine. So basically, the fact that we're only getting 22 images a second in Image J is because Image J is saturating a core. It can't keep up. But if I run this on a faster machine, I've gotten images at more like 80 frames a second on a faster computer. This is not a high performance machine. Yeah. Oh yeah.
Yeah, sorry. When you drew the line through the bright spot before and got the Gaussian bit there, that was all done within Image J? So
Correct.
when you were doing anything that would automatically save a file using area detector, that information would not be written to those
That's
files,
correct.
right?
That's correct.
Okay. And the other question is also related to that. Is there a way that it can do a reverse Gaussian? Because a lot of times, we do absorption markers in the images.
Yeah.
So our peaks would effectively be negative instead of positive.
That's a good question. I don't know. I mean, I only put that in Area Detector because I thought it was a very useful little tool, that Gaussian profiler. It was written by a guy at the APS, and then he left and his code was almost lost, and I resurrected it and put it in the ImageJ GitHub repository just so we'd have a place to keep it. And it's a useful tool, but it needs a little work. For instance, you can make a vertical profile, but the axis it displays is incorrect. The dimensions of the axis, so that needs to be fixed. There's some things, but we have the source code. It's just simple little Java source code that can be easily fixed and enhanced. If it doesn't do a negative Gaussian, we could add that. It's easy to do. Okay, let me see what's my... So with this one, let's... let me just show you that on that PVA plugin. So right now we haven't. It's running at the full rate, right? It's trying to do like 80 frames a second. So let's just set this to a minimum time of 0.1. So now this is only doing 10 frames a second instead of whatever it was doing, 80. And now this guy is keeping up, right? It's running at it can keep up at 10 hertz. So, I mean, that's sometimes a useful thing to do because I've now probably reduced the CPU time on the system significantly. And do the users really care that this is only running at 10 hertz? Probably not. So slowing this down is often a good thing to do. Saves you network bandwidth and CPU cycles with. Because I might want to still be saving at 100 frames a second. That's right. The cameras and all the other plugins, if I haven't slowed them down, so the camera's still doing 83 frames a second. I'm just only updating that plugin at 10 hertz. I should just for completeness, let's go back to that PVA plugin. Obviously, if I disable it, then the array rate over here goes to 0. I can enable it. What are some of the other? Reset that counter to 0. This has not dropped any arrays. think that's enough. You've already seen how we could have changed this port here instead of getting its data directly from the camera to get it from the process, from the transform plugin or the region of interest plugin. I mean, one of the things that you can do with the detector here is, we're reading out the whole detector. But as well as using the region of interest plugin, we can tell it, don't read out the whole camera, only read out, let's say, 400 pixels in X and 300 pixels in Y. And so now we're just reading out part of the camera, which allows us, let's say, if we go to a millisecond exposure time instead of 10 milliseconds, now it's running at 500 frames a second. So by only reading out part of the detector, I can speed up the frame rate a lot. If I go back to read, and I can change also the offset. So that was starting out at 0, 0, but I could start it at pixel 100 in X. Move that readout region of the detector around. Different detectors speed up by different amounts as you do that. Oh, here's another thing to note. See, I told it to make a region here that was 400 pixels. But in fact, see, for all these EPICS PVs, this is what you asked for, and this is what you got. And so I asked for 400 pixels, but because of limitations of this hardware, it can only do a quanta, I think, of 16 pixels. And so it changed my requested value to the nearest one it was actually able to do. So now I'll put that back to 19. So I'm still using a millisecond. It's doing 500 and it's jumping around, but up to 580 frames a second there. If I go back to 1920. Okay, so interesting. See, even with the full width, it's still able to do 580 frames a second. So making the camera smaller in this, making the readout region smaller in this dimension doesn't actually speed it up or slow it down. It's only the other dimension that affects the speed. And that's true. This is a CMOS camera, but that's often true of CCD cameras as well. If you only read out some of the rows, it's faster. But it doesn't matter. If you read out fewer columns, it doesn't speed it up. So if we go back to 1200 here. Okay. I just want to show a couple more things on the statistics. Let's go back to 10 milliseconds. You see, now ImageJ had auto-scaled this when I changed the dimensions, and it's only going up to a maximum of 60 counts per pixel. So that wasn't a problem with it being overexposed. It was a problem with ImageJ having the wrong contrast. Okay, let's open the statistics plugin here. So we've got the net counts, we got the centroid. Here's the histogram. So if I plot it, that's area detector coming up with a histogram. This is ImageJ coming up with a histogram, and they look pretty similar, right? But area detector is doing that in real time, and you could be reading. This is just a waveform, an array that you could be reading into your software as well. And so now let's look at a time series. So if I open a time series of the total counts in this image, and it's doing about 56 frames a second. Oh, that's what the statistics plugin is able to do. See, it's not able to keep up. The detector's going faster than that. Close this before I get too many. Okay, so now if I've asked for an array of points in time here, 2048 of them. So if I say erase start, it's now showing me this is a plot of the total counts in the image as a function of time. And if I put my hand in front of the lens, then it goes down. And so this is a way that you could write a fast scan and collect time series information on the centroid or the net counts or total counts or something like that without, as I said before, without having to have your client read this number 56 times a second and then just read out this array at the end of the scan, and you've collected a scan using a detector, using some statistic in the area detector as your detector, or the thing you're plotting, measuring. You can get here, we can calculate the average. So this is now the average profile in the x direction. And we can look at the average profile in the y direction. Okay, so we can see that this statistics plugin isn't able to keep up. The detector's running at something like 95 frames a second. This can only process 57 frames a second. How could we process more? If we open the more screen here, and we say that right now we're only using one thread in this plugin. But we've configured it, and you configure it in your startup script. It's configured to use up to a maximum of 5 threads. So if I just increase the number of threads here to 2, all of a sudden it's able to keep up, because now it's doing, it's got 2 threads running in 2 cores that are between them able to keep up. So if I look at my CPU time here, it's around 66%. If I go back to 1 thread, it drops down to about 50%, 47%. But we have CPU to spare, so I can throw another thread at the problem, increase that to 2. CPU time goes up, but now we're not dropping any frames. We're keeping up with the detector. If this was a plugin that was processing the data, it's possible it would put out the arrays in the wrong order, right? Because the 2 threads are running asynchronously, and this one might get done processing the previous frame after this one got done processing the next frame. So there's an option here to sort the output. So there's a buffer, and it puts the frames into this buffer and then rearranges them so that they go out in the right order as determined by the unique ID here. It looks at the unique ID and outputs them in the correct order. It's a little complicated because it's possible that the next frame that it's supposed to put out will never arrive, right? Because it got dropped somewhere else. There's a missing unique ID. So if that's true, you can set the size of this buffer and how long are things allowed to sit in that buffer before you give up and ship them out anyway. Yeah?
I would say that you want to sort them all the time. Why would you use unsorted processing?
Because you may not care. You may say, I don't care. I know what the unique ID is. They're going to end up in the file, and I know the unique ID. I don't care if they're in the right order. And because this introduces additional latency and processing to do this. So, yeah. There was another question? Yeah.
Well, is there a disadvantage to going up to more threads? What's the disadvantage?
There's no disadvantage, except that you run out of cores, right? I mean, there's no point in throwing more threads unless you have more cores. And this is only a 4-core machine, right? So it wouldn't make sense to go to 5 threads because then they're just fighting each other.
From 2 to 3, though, would it be the same?
And from 2 to 3, it shouldn't make any effect. It shouldn't affect the CPU time. because it's already keeping up. But if I ran faster, then I would need 3 threads to keep up. Okay. Okay, I want to get, before we have to stop here, I'm getting through this fairly well. We already saw the transform plugin rotating and stuff. Okay, it's the file plugins that I think are most important. So let's go look at those. So the first one I want to do is the simple TIFF plugin. So I've got this configured to write to C data TIFF, file name of test. I'll make the next file be number 1. And this plugin right now is enabled. The execution time here is very fast. It's like 15 microseconds, but that's the time to do nothing, right? Because this file saving hasn't been started, it's basically just getting a call back and doing nothing. So that only takes 15 microseconds. But if we actually start saving, that number will go up. And so it's going to be start with file 1. It's auto incrementing. The file format %s just means combine those 2 strings. Underscore %3.3d means make it the first file be 001, 002, and so on, and then .tiff. So right now it's configured in single mode, so I can just say save, and it just each time I click it, it's writing out a TIFF file. And if I say auto save yes, now it's writing them as fast as they come in. Let me say auto save no. Okay, so that wrote 280 files. You can see why you don't want to turn on autosave necessarily. You can also do this in stream mode. And let's say I want to capture 10 images. Then, so you change it to stream, and you say how many images you want to capture or stream, and hit start. And now it just did 10 files. So let's do set this to test underscore A, and set this back to 1, start. So now, the last file it wrote was test underscore A010. So now let's go look at one of those files. There's a utility that I'm running here that's called TIFF dump and TIFF info. So if I go /TIFF and I do TIFF info test underscore A001. Okay. So it's telling me that this is 1920 by 1200 image, 8 bits per sample, and this is some sort of standard TIFF tags. But then down here it says the software was EPICS area detector. That's a standard TIFF tag, and then these things tags 65,000 to 6503. Those are binary information containing, respectively, the timestamp as a double, the unique ID, the timestamp in seconds as an integer, and the timestamp in nanoseconds as an integer. These two together are a more precise timestamp than this, but a little more complicated to use because it's seconds and nanoseconds instead of just a floating point number. So you see that this TIFF file does contain additional tags which were written there by Area Detector. I also have for point gray, I've got an attributes file like the one we looked at for SIM detector. So I'm going to say point gray attributes.xml. Okay, and now it said it read the attributes file. Okay, so previously it wasn't using, there were no additional attributes beyond the stuff that's always in the ND array. But now it is putting additional attributes in there. So now if I go to the TIFF plugin again, and let's change that to B, and back to file number 1, and stream it again. So now we just saved 10 more files, and let's do TIFF info on B001. Okay, so now you see there are additional TIFF tags in there. So these are the ones we saw previously. Color mode is something that wasn't in our attributes file, but the driver itself created a tag that basically says this is mono data. Color mode 0 is mono. But these are all the things that we added as attributes in that attributes file. So you see it stored the acquisition time, the image counter, the dimensions of our detector, the model, Grasshopper 3, the name of the attributes file itself, the manufacturer, and pi and e. These were the things that were written by those functions that I wrote 7 years ago, blah, blah, blah. Okay, so that's what I wanted to show you for the TIFF plugin. Now I'm going to do oh, and let me just go to C data TIFF and take one of those TIFF plugins and just drag it into ImageJ here, and it opens up in ImageJ. So let's go instead and open the NetCDF plugin, file plugin. It's the first one. There it is. Okay, so we're going to put this in C data /NetCDF. And again, test. And I'm going to do this one just in stream mode, and let's save 100 images. Okay, so that just wrote 100 images into a NetCDF file. In ImageJ, there's a NetCDF plugin, so you can say load NetCDF file, and we'll go to data NetCDF. This guy, you see that was actually, well, that's probably like a 200 megabyte file. And then it comes up and it shows you all of the data that's in this file. There's all sorts of variables in this file. A lot of them are the attributes. What we want is this one that's a 3D array called array data. So it's 100 by 1200 by 1920. So these ImageJ's array indices are the opposite of C. So 1920 is X, Y, and the number of frames. So if I select that one and say OK, it just read in the 100 frames, and they're now an ImageJ stack. So as I drag this, the second hand, it's hard to see, but the second hand is moving. Okay, so that's, and then there's also a utility that you can run with ImageJ. So let me go ... netcdf. There's a utility called ncdump -h, means just show me the header. Okay, so this is a dump of the NetCDF file. Tells me the dimensions that are present in the file, the data, the global attributes, and all the data. And so we could plot out or print out all these different values of the attributes in here, be they strings or numbers or whatever. And then finally, you could do the same thing with HDF5. So there's an HDF5 plugin here. it's writing its data to CData HDF5. Let's start with number 1, and we'll stream again 100 images, and start. Okay, so that just saved 100 images to an HDF5 file, and if we go over here and go to HDF5, yeah, so it's H5 dump minus contents, for example, test underscore 001 dot, 000 dot H5. That was the one we just did. So it tells you, it shows you here all of the data sets that are present in this HDF5 file. If you do, instead of minus contents, if you do minus H, that shows you the header. That shows you sort of more information about the structure of the HDF5 file. But then there's this nice little GUI program called HDF view. And you can say file open, this one. So you can browse it. And so you can say, look at entry, instrument, ND attributes. So this is like the timestamp in seconds. If you double click it, you get a table view of those. If you look at the nanoseconds, double click it, get a table view. Those are all different. The unique ID, those should be going up by 1 there. And is this not the one we just did?
This is just for the afternoon.
Oh, what's the one we just did?
001.
11:05 a.m. in my computer. Yeah, okay, so let's read that one because that has the right attributes. File, close. Oh. Thanks. Yeah, now there are a lot more attributes in there, the ones that we added. But if we look at the detector data, it tells us, again, this is 100 by 1200 by 1920. And if we double click on it, we right click on it and you say open as, and then you can say image. And these are, yeah, that's right. Is that right? Oh, no. The height is dim 1, the width is dim 2, and the depth is dim 0. Yeah. So there's an image, and there's the first image, and we can step through them with this. We're clicking through the images here. Second hand is moving very, very slowly because it only took 2 seconds to go. I didn't do all the plugins that I was hoping to do, but the process plugin, you saw how it, the kinds of things it can do on that during the talk. The region of interest plugin, let me just show the overlay plugin. That should just take a second. We got a break soon. So let's kill that. And so if we go to the overlay, so this is enabled, and so this is showing the definition of a bunch of up to 8 different overlay elements, and each element can either be a rectangle, it can be a cross, a rectangle, an ellipse, or text. And for each one, you can say, do you use it? And then you can say, where is it? The X, position or center, width and size. Same thing in Y. And if we go to this first one, this is the full definition of this first overlay element. So you got the shape, how you draw it, what the red, green, and blue color is. Because we're working in mono, only the green is important. If it was text, you could do this, and including controlling like a timestamp that it would print out the image, what time it is. But what I want to show you here is that this guy, this first region of this first overlay here is getting its position from the first region of interest, and getting its size from the first region of interest. So if we change the PVA plugin to be getting its data from, instead of PG1, get it from over 1, it's now, and there's exactly the problem Kaz was talking about, that the, you see this image, this is supposed to be a rectangle, but we're only seeing half of it because it's disappearing because this is being binned down. It's not displayed at full resolution. If I zoom it up, now we see the whole thing. But let's say we wanted to see it like this, but not have the box disappear. What we could do would be to make its width here, instead of being 1 pixel, let's make it 2 pixels. Might even need to be more than 2. That filled that one, but I think if we go to 3 pixels, yeah, now we see the whole thing because it's fat enough that it doesn't average, it doesn't disappear. But now if I open the first region of interest and change where it is, so I go to ROI 1, so this is now at 247. So if I change that to 400, that box moved. And if I change the vertical position from 399 to 200, it moved. So, this overlay is tracking the definition of this region of interest. That wouldn't have to be the case. I could go to the next one. Let's see one down here. So I can make a cursor. I want to display this, and I want it to be, its center to be at 400, and its width to be 100. No, not its width. That's just 3. Its size to be 100. And in X, make the position be 300, and its width 3, and its size 200. And let's make that a cross and change its color again to be 255, so it's white. Yeah. So now we've made another element there, and we could change its position by just moving. I just got my finger on that slider bar there, and we're moving that overlay across the image. And it's getting late, so I won't actually show you how this works, but I'll just show you that you can do it that there's an EPICS, well, make a box here and say EPICS AD controller, and I haven't got this all set up, but what you could do is this lets you, this is set up for the SIM detector, but you could, this box that I drew in ImageJ, you can tell it, write that box to be the readout region of the camera, right? And it would write to the camera and set it so it's just reading out that region of the detector. Or you can say, I want that to define ROI 3, and it would define the region of interest graphically. Or you can say, I want that to define an overlay. And so it's nice, instead of having to type the numbers on this screen like I was just doing to define those things, you can just do it graphically and hit the button and define it graphically. You just takes a second to set this stuff up, and I don't want to go through that now because I'm keeping you from your lunch. All right. Any more questions? Everybody's hungry. Yeah.
Very simple one. Can you keep the image mono, but say you wanted to change your rectangle and make it red? Is it possible to do that? Or just
Yes. What you need to do is you need to take the image from the camera, put it through a color convert plugin that changes it from mono to RGB. And then this works on the RGB image, and so now you can make this be red and green and blue. It does mean that downstream of that plugin, you got 3 times as much data. And you probably wouldn't want to run that to your disk file, but you can run it to the screen, so that the cursors look nicer because they're in color. Yeah, that's a really good question. That's a good thing to do. And that the color convert plugin lets you do that. And it won't affect, this will still be mono, right? I mean, it'll be equal amounts of red, green, and blue. Yeah.
Are you still developing more plugins? Or there's a method for creating plugins?
Oh yeah, there's documentation in Area Detector on our homepage about guidelines for writing a new plugin, and how to do it. I haven't written a new plugin for quite a while. I've written a lot of new drivers, but not new plugins. But I've been fixing, like one of the things that was added to this plugin. You used to be only able to control the position, which is the upper left corner, and that's a pain. Usually, I mean, a lot of times it's more you want to describe the center and the width, rather than the left corner and the yeah. So that kind of stuff gets added. But yeah, it's the whole idea of the plugins is if you've got a domain specific problem that there's something that you want to do that maybe it's not general but it's useful for you, then just write your own plugin. It's not hard to do. I mean, a lot of these plugins are they're 200 lines of code, 300 lines of code. There's not a lot to them. The base class takes care of all the stuff about, minimum time and all that stuff. You just have to write what's the function that gets executed on each new array, right? And the thing that makes it a little trickier is that you should write it using what are called C++ template functions, meaning that it'll work on any data type. It isn't limited to running on 8-bit integers. It can handle any data type, assuming that your domain specific problem needs more than one data type. And if it doesn't, then don't make it more complex than it needs to be. And there are lots of examples, right? You can just look at an existing plugin to get ideas of how to write a plugin. Anything else? All right, we'll see you in the labs tomorrow.